what happens? We add this ketone to acid, presence of bromine. Based on the overwhelming answer of this is the answer, let's go through it more slowly. What is the most reactive thing present? Okay. So the hydrogen ion, which is our acid. So what do we need to find? Find something remotely basic. Where's the best base? The oxygen. So we can have our oxygen share lone pairs. And we'd end up with this structure. Does oxygen want to be positive? No. So what does it do? Okay, so it could break the double bond, or it could get rid of the hydrogen. So it's an equilibrium reaction. So if it breaks the double bond, takes both those electrons, and we would end up with this species. What is the relationship between those two drawings? They're just resonance structures of each other. So that's cool. We have shifted the positive charge off of the oxygen, but we've also shifted it to a carbon, which is now a bad Lewis structure because carbon doesn't have its octet. Okay. So what can we do? So we do have bromine floating around. Is the bromine nucleophilic? It's horribly unnucleophilic. The only way it can become nucleophilic is if we make it bromide. Well, but to make it bromide, I'd have to have a bromine cation form. Bromine cations aren't particularly stable. Okay, so I can't get the bromide. Any other ideas? Nope. And we would form H+. H+, something that's okay to have in our solution? We started with it, sure, why not? What did I just make? The enol. Is the enol stable? No, it is very reactive. And it favors the keto form. Whoops. Drew my arrows the wrong size. But what is now unique about our enol? What do we have? Say that a little bit louder. We now have a nucleophile. Do we have something electrophilic in solution? What's that electrophile? We have our bromine. And the result is that we have done a substitution at what position? The alpha position of a hydrogen for a bromine. Under acidic conditions, it pretty much stalls out here. Okay. And the reason being is that the whole reason this whole cascade started was because we could protonate our oxygen, and then that made that extra hydrogen acidic. Well, the issue with bromine is that with those electrons, it can stabilize and prevent the enol from forming, so our reaction stalls after one substitution. We can't actually do anymore because we end up generating a structure that is less acidic than we started with. Okay? This was way back when, chapter 10. What happens if we erase all that and we switch it now to hydroxide? What was that? We do the exact same thing. Nothing's different. Instead of now it being an acid-catalyzed enol formation, it's a base-catalyzed enol formation, and technically an enolate. So when we form our enolate, this can now act as a nucleophile, react with our bromine, just as before. There's lone pairs all the way around there, but I'm getting tired of drawing them. And we would form this fun little structure. What is special about this molecule, say, in comparison to our starting material? What's that? We do have a leaving group. What else? We still have an acidic hydrogen. Even further, it's more acidic than it started with. Why is it more acidic? There's an electronegative element attached to that carbon, which is now going to withdraw more electron density away from the carbon, which then makes the carbon draw even more electron density away from the hydrogen. This whole mechanism started because our starting compound acted as an acid. Our product, or if you will, our first product, is now a stronger acid than we started with. So what happens? It continues to react. And it will continue to react until eventually we end up with our fully substituted structure. That's a BR, right? Questions about that? Within the context of this chapter, this seems like a bit of a silly reaction to look at, because in this sequence of chapters, what we're looking at is the addition and elimination mechanism. Well, we haven't done an elimination here. Okay, so why are we looking at this reaction again? What happens if we change our starting material? Right. Oh, shucks. Go away. You didn't see any of that. Or the answer. What happens when we add sodium hydroxide and bromine to that starting material? We're going to do the substitution. And we're going to continue to do that substitution until I've completely, fully substituted. We now have an interesting thing that just appeared here. What is now special about this molecule? We now have a leaving group. Well, do we have a nucleophile? A leaving group is useless if we don't have a nucleophile. Hydroxide is a nucleophile which can attack. We would form our tetrahedral intermediate, and since there were questions on how many steps this was, I'm going to stop showing shortcuts, much to my dismay. We now have our tetrahedral intermediate. That tetrahedral intermediate can reform our pi bond, kick out our leaving group, and we would end up with this species, and this one. Okay, what product did I just make? What do you mean strong nucleophile? I'll accept that.
Oh, you have a lone pair on the carbon, it's pretty reactive.
Lone pair on the carbon could act as a nucleophile, so this is technically an equilibrium reaction. That takes us right back to an unstable intermediate. With our equilibrium dynamics, we will be pushing to the formation of the CBr3. This species, not only is it a strong nucleophile, it could also act as a base. That can deprotonate our carboxylic acid, forming an incredibly stable negatively charged oxygen. That's what drives this reaction forward, because a negative carbon is a horrible leaving group. Okay? It's not bad, but it's really not good. Okay? So once that has been kicked out, we can do that secondary chemistry of our acid-base reaction, form the carboxylate, and then what would be known as bromoform. CHBr3. Well, which structure do you think we actually want to obtain? The one with one carbon or the one with a whole lot more carbons? The one with a whole lot more carbons. Well, that species is currently a negative charge. What can I do to neutralize it? I will add acid as a second step. Why do I have to add it as a second step? Why not just start the whole thing off with just acid? Why won't it react? It'd only do the single substitution. Okay? So it wouldn't get us all the way through the reaction. Even further, why would that be problematic? What would your nucleophile be if we ran under acidic conditions? Water would end up being our nucleophile, and water is a weak nucleophile. Would a weak nucleophile be able to force out a relatively bad leaving group? No. Okay. So under acidic conditions, we can't push this reaction along. So we have to run it as two steps. Questions? Within the context of the reaction, we end up with a carboxylic acid as our final product. What product do we get with this one? Let's do that. As a hint, you guys are clearly more tired than me. Okay. Mirrored conditions. How about if we did, it's a little bit crowded there, a benzene ring. What would we get then? End up with our benzoic acid. What do these things have in common? They all have a methyl group that is alpha to the carbonyl. This chemistry, while it looks a bit crazy and maybe a bit nasty to go through, turns out it happens really, really quickly. Okay, so it's a very fast reaction. It is so fast that if we're trying to understand something about an unknown compound that we're working with, we can just throw some base and one of our halogens at it. It's typically iodine. Okay, and we just look to see if a precipitate forms. What would that precipitate be? Well, iodoform is highly insoluble in aqueous environments. So what ends up happening? We would see a precipitate, okay, for that other species, okay, the one that we end up not isolating. Okay, it's typically the HCI3. That precipitate now tells us that whatever we started with, there was a carbonyl and a methyl group right next to it. I now know some information about that unknown compound. And because it is a fast reaction, this is literally take a few drops, throw in some base, throw in some iodine, boom, there it is. I now know something about my structure. Okay, in a matter of seconds, we've got information. The lab that we're starting for the next 3 weeks is based on this same general concept. Okay? What we are working towards is classifying our compound as quickly and efficiently as possible. This is known as a classification test. Super famous or super common type of question to show up on the ACS exam because they have you go through and run a bunch of these classification tests. So the question that you might see would be which of the following would give a yellow solid when mixed with iodine and sodium hydroxide? Right, well, what would we look for in our compound? A carbonyl and a methyl group, alpha to the carbonyl. Right? Done. There's the answer and move on. Okay. Not a huge fan of the question because ultimately it's really coming from just memorization. Okay. Yes, you could go through and draw it out, but if they're giving you 4 answers, you're drawing out 4 reactions to see what those products are and could you possibly make HCI3? That gets a bit of a tedious reaction to ask if you're expecting somebody to work with it as opposed to just straight up memorize it. Either way, it's still a common question. So anything that happens quickly, zinc chloride in the Lucas reaction, you vaguely remember that one, is also a very common reaction to use. Because what that tests for are alcohols. So anything that can be classified or named a classification test, you should watch out for those because those are super common on the ACS exam. Okay? The overall reaction is referred to as a haloform test. Okay. Haloform because we are forming our product, which is classified as a form name. I'm not quite sure why we refer to it that way. And the halo because it works for any one of our halogens. You can form chloroform, bromoform, or iodoform. Okay? Questions about that? Is that all review and that's why you're staring at me blankly? You're still staring at me blankly, so I'm not sure that was... Is this thing on? Am I actually saying something? There's our big long mechanism if you wanted to look all the way through that. After that, what we'll move into would be our hydride nucleophiles. We've seen these before, sodium borohydride, lithium aluminum hydride. And previously, we really didn't see a difference between them. They both did the same thing. They reduced our aldehydes, they reduced our ketones, and we ended up with the same product, and we really had no reason why we would choose one over the other, because they both did everything. Okay? Well, what happens if we take, say, sodium borohydride and try this reaction on this acyl chloride? What product would we get? Sodium borohydride supplies what? Hydride. Hydride acts as nucleophile. Sodium borohydride and lithium aluminum hydride do not act as bases. Okay? They are hydride nucleophiles. Okay, so what happens? It attacks the carbonyl. We break the pi bond. Why do we break the pi bond first? Don't all shout it out at once. Why break the pi bond and not, say, the chloride? Pi bond is higher in energy than our sigma bond. So we would expect our tetrahedral intermediate. What happens with that tetrahedral intermediate? Well, the electrons come back down and kick out the leaving group. And we end up with, good answer on the functional group there, an aldehyde. Ta-da! What's the issue with an aldehyde? It can be reduced, but only in the presence of a reducing agent. Do we have a reducing agent?
Yes.
Say like the sodium borohydride we just added? Yeah. Guess what happens? It gets reduced again. Okay? So this is the same kind of issue we just saw with the haloform. It can react once, but then we end up generating a more reactive species or an equally reactive species. So it reacts a second time. And the end result, come on now, is that we end up all the way down to the alcohol. Okay. Well, does this happen with lithium aluminum hydride as well? Yep, does the exact same thing. Okay. What happens if we change our electrophile, though? Okay, so in this case, it's an acyl chloride. But what if I had used, I don't know, how about an ester? That's a C. What is the reactivity difference between the ester and the acyl chloride? Is there a reactivity difference?
Less reactive.
Why is it less reactive? It actually has nothing to do with the leaving group being less stable, because the issue happens before we even get to the point of a leaving group. Electronegativity, oxygen is more electronegative than chlorine, so I'm not quite sure I accept that answer. When trying to predict something about reactivity, where do we start? Size. Okay, the atom's holding our charge. Well, neither of those atoms are really holding charge. Okay. We could look at electronegativity, but again, neither of our atoms are holding charge. Okay. What are we looking at? A resonance effect. What is that resonance effect? Oxygen can donate electrons in. And this is where we could potentially run into a weird gray area. Can chloride donate resonance or electrons in? Not really. Why not? It's not too electronegative, though. That's one of the weird things, because oxygen is more electronegative than chlorine. So this is that counter argument. There's something weird happening here.
Its electrons are in a higher energy orbital, so it can't share them efficiently.
Why can't it share
Because
them?
they're, for resonance, they should be at comparable energy levels on the chlorine.
Yeah, no, I can see your argument, but that's not going to be an easy one to look at. I'd like a probably less correct answer, but an easier to see or visualize. How many bonds do your halogens have? One. How many bonds can oxygen have? Really? Only two? Oxygen? H3O plus? 3 bonds? Yeah? Oh yeah? Okay. Oxygen, in this case, when it shares its electrons in, would have how many bonds? 3. May not be happy about it, but we know that exists. Chlorine donates electrons in. 2 bonds. How many times have you seen chlorine with more than 1 bond? I'm really hoping you all keep your hands down. Okay. Very, very rare for our halogens to form more than 1 bond. Okay. So we can use that less correct answer to help us evaluate what's happening here. Both of them have lone pairs. Chlorine is not going to be able to share those electrons as efficiently as the oxygen, which means that resonance contributor does not exist. What does that do to the reactivity of the acyl chloride in comparison to the ester? It makes the acyl chloride more reactive, more electrophilic. The ester has a resonance stabilizer that prevents it from acting as an electrophile. Okay, neat. Straightforward on that one. So let's take it to the next level. Aldehyde versus our ester. Which is more reactive? Okay, so we're hearing both answers here. Why are you saying the aldehyde? It's the same argument. Resonance. Resonance on the ester does what to its stability? It makes it more stable, which means what happens to the reactivity of the ester versus the aldehyde? It goes down. So if we look at our reactivities, the acyl chloride is the most reactive here, followed by our aldehyde, followed by our ester. Why does that become important when we now look at the reactivity of sodium borohydride? It reacts readily with our acyl chloride. It reacts readily with the aldehyde. As soon as we hit the ester, we've crossed a line in the reactivity of the species, and it does not react with the ester. Okay. And here's where you'll love me on this. At least not efficiently. Which means when we're looking at an individual reaction and say we want to reduce an ester, sodium borohydride is a bad call. So you can pretty much just cross sodium borohydride off the list for ester reduction. Okay. It might be nice if someone had gone through and compiled a bunch of these. Well, they have. Okay. We've got two columns here, the reduction of sodium borohydride versus reductions with lithium aluminum hydride. You'll notice that lithium aluminum hydride all the way through completely reduces out. Even when we get to the amide, and this one's a bit weird, because if you look at the product for the acid chloride with lithium aluminum hydride, what product do we get? An alcohol. How about the next one? Alcohol. Esters? Alcohols. Acids? Alcohols. Amides? Why is it not an alcohol? We're reducing away the carbonyl. You get rid of the carbonyl in all of these cases. The first case, you can reduce away your carbonyl. We lose the leaving group as our aspect. We'd end up with an OH. Next deal, we lose that whole piece, OH. This group, lose it, lose it. We'd have our OH. What happens at the very end? What happens when you get rid of the carbonyl? You have a nitrogen left over. Why would we kick out the nitrogen over oxygen or not kick out the nitrogen over oxygen? Which is more electronegative? Oxygen. Which one wants to hold all its own electrons? Oxygen. So we end up getting our amine out of that result. If we go through and look at those same reactions with sodium borohydride, what do we notice? Well, the acid chloride works. The acid anhydride also works. And this is where they drop in the ester, and it's a bit misleading because they show primary alcohol as a product. And we just said, well, that's a horrible reaction. What do they have in that weird grayed out font right above the reaction? This reduction is very, very slow. Right? Slow enough that we do not expect to use sodium borohydride to reduce esters. After that, when we move into the acid and say the amide, we get no hydride substitution, okay? Or nucleophilic attack. Doesn't work anymore. Why does it not work anymore? You'll notice that the carboxylic acid, it says absolutely straight out, no reaction. Whereas the ester said it did kind of. What's different about the acid?
Resonance stabilized, super resonance stabilized.
We do have that hydride floating around that does primarily act as a nucleophile. It's our only real source of hydride nucleophiles. Can it still potentially act as a base, say, in an extremely acidic environment? Yeah, that's actually how we neutralize our sodium borohydride reactions. We added acid to them. What is the functional group of a carboxylic acid? It's an acid. So what happens? We add the sodium borohydride. It removes the hydrogen. Now what's the problem? Why is that species even less reactive? We'd now have a negative charge on the carboxylate salt. The carboxylate stabilizes the electrophile even better than the ester. So it becomes even less reactive. Why is the amide even lower reactivity? What's our difference now? Yes, it's resonance. But what's different about that resonance? What atom is doing the resonance? Nitrogen versus oxygen. Which one's going to do better resonance? Nitrogen, because less electronegative. It is more willing to share those electrons. Okay? So if you go back and look at the old tests, one of those test questions listed a whole bunch of reducing agents, said which one should you use to do this reaction, okay, and you had to pick one of them. You now have the ability to pick one of them because we now have a difference between sodium borohydride and lithium aluminum hydride. Up to this point, there was no way to distinguish them, except that lithium aluminum hydride was a whole heck of a lot more reactive than our sodium borohydride. Why was it more reactive? There was an electronegativity issue happening between aluminum and hydrogen versus boron and hydrogen. Okay. The larger difference in electronegativity between aluminum and hydrogen makes that bond more polar, which makes it then more reactive. What other reasons? The next one's trickier, much, much trickier. Size of aluminum versus the size of boron. Okay. What's our difference there? Aluminum is bigger, which means the hydrogen, or hydride, is now where? Further away, which makes it more reactive. It's easier to get access to. The last, absolutely hardest one, which is actually what I was fishing for, but the size worked. What's the last difference between sodium borohydride and lithium aluminum hydride? A counterion. Sodium is larger than lithium. What does that mean? The lithium will stabilize or polarize your carbonyl oxygen much better than the sodium does. If the carbonyl becomes more polarized, what does that do to its reactivity? It makes it more reactive. Okay? So all sorts of features stack into that one to make lithium aluminum hydride more reactive. Okay? It's a good question. Can we continue to tweak our sodium borohydrides or our lithium aluminum hydrides? Instead of doing lithium aluminum hydride, could I get a little bit more reactive and say maybe reduce an ester by doing lithium borohydride? Remember, the lithium polarizes more. It polarizes the electrophile more. So that makes the electrophile more reactive. So if I switch to lithium borohydride, it should increase its reductive ability. And sure enough, it does. Could we change the hydrides? Instead of just doing 4 hydrides, put on some other groups that help polarize that boron or sterically hinder the structure. Is that going to change the reductive ability? Yep. And in fact, that's going to be in one of our next 3 or 4 slides. Okay. So why barely are esters? What we're ultimately looking at, as we've already kind of discussed this, is that resonance stabilization that starts to appear or have a significant effect with our esters and our amides. We don't see it as much with the acid chloride or the acid anhydride. Okay, why not? The acid chloride we just addressed. Okay, we came up with kind of a piss poor example, but it works. Chloride only wants 1 bond. Fine. Okay, so that makes sense. Chloride should be much more reactive than all the others because it can only form 1 bond, so it can't do reasonable resonance. But what about the acid anhydride? Okay, if that's the carbonyl I'm looking at, isn't that resonance stabilized by that oxygen just like the ester did? Why is the anhydride so much more reactive? Because if I'm looking at that carbonyl, that has the exact same resonance option. What's that? If the oxygen is doing resonance towards the left, what is it doing towards the right? We can only move 1 pair of electrons any given instant. So what happened to our carbonyl to the right? It just became more electrophilic. Okay. So when we're looking at a nucleophile coming in, what we tend to lose focus on is that there's 2 parts of this molecule. There are 2 electrophiles. One of them is resonance stabilized by that oxygen. The other one is not only not stabilized by that oxygen, but if we do a resonance structure, what charge does that oxygen become? Positive, which means what is it doing to the electrons in that bond? It's sucking them further away, making our electrophile even more electrophilic. Okay. If we push that even further, what would our leaving group be in that case? A carboxylate. Is our carboxylate reasonably stable? Through resonance stabilization. It's a fantastic leaving group. Okay. So when we're looking at these drops in reactivity, it has to do with those resonance effects and the overall characteristics of our molecule. Okay. So if I wanted to say, if I had a compound with an ester and a ketone in it, and I want to reduce just the ketone carbonyl, sodium borohydride is what I will go to, because it won't reduce the ester to any significant extent, right? And I'll end up with primarily my reduced ketone, and I'll have the ester left over. How can I help kind of aid and prevent the ester reaction happening? Make it cold. Notice what temperature are they running at? 0 degrees. That's going to slow things down and prevent things from reacting further, particularly reactions that weren't particularly favorable to begin with. Okay, so if we can cool that down, that helps. What else did they do?
Time.
Look at the time they ran that reaction for. 5 minutes. They shortened the amount of time available for our reagents to actually react. What will they do after that 5 minutes? They will quench the reaction by probably adding a strong mineral acid. That mineral acid will neutralize the sodium borohydride, and now it can't react anymore. Okay? So we have ways to limit exposure of our reducing agents with other functional groups. And all we're really trying to do is take advantage of the difference in reactivity of each of those different carbonyl-containing compounds. Kind of neat. Questions? Okay, let's see. Is this it? No. But lithium aluminum hydride can. Why can lithium aluminum hydride? I'm not particularly happy with how your textbook presents this, because their explanation for why lithium aluminum hydride can react and sodium borohydride doesn't react are completely counter to each other. They say lithium aluminum hydride can do it because it can polarize the carbon-oxygen bond. Well, so does sodium borohydride. Okay? So their explanation doesn't do a very good job separating why one reacts and not the other. So just be aware of that. All you really need to know is that one does and one doesn't. So don't panic on the nitty-gritty detail of it, because it's not the easiest to go through and find. You're ultimately looking at nuances within the energetics of those reactions. Even further, it's kind of an interesting thing. Our carboxylic acid can be reduced with lithium aluminum hydride. This one's even more bizarre. Okay. How do we quench borohydride and lithium aluminum hydride? How do we stop those reactions from happening? Cold, and finally, add acid. What do we start with here? An acid, and what do we end up with? A 95% yield of the full reduction. Okay, why? The lithium aluminum hydride is removing a hydrogen, but then the lithium is helping to pull that negative oxygen and keep that negative oxygen from doing the resonance, which then facilitates the hydride attack. Okay? So the dynamics of the reaction change ever so slightly, allowing the reaction to actually occur. And you end up doing some kind of interesting things along the way. Okay. We just talked about those. We have big differences between the sodium and the lithium ions. We have big differences in the bond length and bond polarity of our hydride metal bonds, or semi-metal bonds. Where are you? Yes?
Would the other, would there be an enantiomer for the other 5%?
Ooh, interesting question. Should there be an enantiomer here?
Oh, wait, no.
No, question's already asked. Okay, and since you clearly now know the answer, you're not allowed to answer. Should there be an enantiomer? So I'm seeing some shakes of the head no. So we'll pull back at some of what you said. Would the other 5% be the other enantiomer? That would suggest that we have a vast excess of one chiral product over the other. And the only way we get a chiral favoring is if we have a lot of chiral starting materials. We really don't have that much of a chiral favoring. We do have a chiral atom, but it's not going to be a huge contributing factor to this. Right? Or at least that big of a discrepancy. Right? Why do I not have enantiomers? Because we changed the bonds. What do you mean I don't have a stereo center there? That is absolutely a stereo center.
Oh, I'm sorry. Talking about the one.
Why am I not affecting the stereo center? No chemistry is happening at the stereo center. The chemistry is happening at the carbonyl. Okay? That's why there's no enantiomer issue. The chemistry isn't happening at our stereo center. It's happening at the other location. Okay? Very kind of common, subtle thing to throw in there. We'll give you some random chiral atom and then say, okay, let's make it all sorts of weird chiral changing and everything. And oh, there's multiple products now. Everybody freaks out and says, oh, I got to watch out for that now. No, you don't. Chemistry didn't happen at the chiral atom. It happened at the other location. So don't panic just because you see stereochemistry. Breathe through it and make sure your chemistry is actually happening at that position before you freak out too much. Okay. Questions? Okay. What would we expect here? Did you say something? Oh. What do we expect for a product? I'm going to say right now, I love the power of technology. Ta-da! There's the product. What happens? The hydride reduces the carbonyl. That's it. Okay. Could we potentially stop it? So if we take a look at an acyl chloride, when we add lithium aluminum hydride or sodium borohydride, what happens? The very first thing that happens is we end up with an aldehyde. Okay. But then we have an aldehyde. What do aldehydes do in the presence of lithium aluminum hydride or sodium borohydride? They reduce, and they continue to go all the way down to the alcohol. Okay. If we took a look at the next one, the ester, what reagent would I have to use to reduce the ester? Lithium aluminum hydride. But what happens when we reduce lithium aluminum hydride or use lithium aluminum hydride? It takes it all the way down to our alcohol or our ether functionality. So we again, or sorry, our alcohol. So this again becomes problematic. What if I want the aldehyde? So we could try and do a protecting group, but you're still trying to put on a hydride, so that's going to be problematic. Maybe we should use some kind of reducing agent that has been poisoned and prevents it from reacting with the aldehyde. Do we have such a reagent? Yes. Two big ones get popped out, and this is what you were referencing earlier, Cassie, is what happens if we change our structure. So the very first one, lithium aluminum hydride with 3 tert butyl groups, or 3 tert butoxide groups. Okay, so if we drew that one out real quickly, it probably won't be that real quick, but I'm going to attempt. We still have that hydrogen-aluminum bond, which is still a metal-nonmetal bond. That is effectively a hydride. So this species still can supply hydride nucleophiles. But it has all of those oxygens around it. Well, what are those oxygens, and for that matter, the T-butyl groups doing? They're putting enough electron density around there that it can sterically block that species' reactivity with the aldehyde. Okay. The aluminum has so many electron donating groups in it from the oxygens that its coordination to the negative oxygen intermediate, not that strong. So it doesn't polarize the bond very well. It's sterically hindered so much that it also makes it very difficult for it to actually get into to react with the aldehyde. Why does it react with acid chloride then if it's sterically so sterically encumbered? What's so special about the chloride, the acid chloride versus the aldehyde that would allow this steric monstrosity to make it in there and react? What's that? So it's referencing our leaving group. It's a little bit more important than that. What is the reactivity of our acyl chloride versus the aldehyde? Much more reactive. The reason that species can even get in to do the reaction is ultimately coming back to the reactivity of our acid chlorides. Our acid chlorides are insanely reactive. So what we've done is built a structure that can still overcome that insanely reactive issue, okay, but then can't deal with the slightly less reactive aldehyde. What other things have we done in this reaction to help prevent it from potentially reacting more? Notice again our temperatures. The temperatures are very, very cold. Negative 75 degrees Celsius is not a pleasant temperature. Right? So by keeping it cold, we are trying to prevent and minimize some of those other reactions. The next reagent is known as dibol, though for whatever reason they decided to not show the L. Any ideas what dibol is? Diisobutyl aluminum hydride. So we have our isobutyl groups and our aluminum hydride. Those isobutyl groups, again, help sterically interfere a little bit. Will also run at lower temperatures. We do have an issue because our ester is less reactive than our aldehyde. But what ends up happening is in the intermediate of the reaction, the aluminum structure ends up stabilizing some of those intermediates, and we end up forming what is effectively a hydrate. Okay? The hydrate or acetal-ish version of our intermediate won't react with the dibol, and it stalls out until we wash all of the reactive species away, and we'd be left with the aldehyde. End up taking advantage of the weak equilibrium with our hydrate species. Okay. Again, notice temperature, very, very cold. Okay. So both run cold. Did I really draw that? Oh, I drew sec-butyl. Dang it. This is isobutyl. Sorry, I drew the wrong one up there. This is isobutyl that's drawn here. I drew sec-butyl on the previous page. I knew something didn't look right. Okay. Just not that big of a deal, but that's your difference. Okay. Both of these are still hydride suppliers, hydride nucleophiles. The big difference is that we can now stop the reduction without continuing on. Okay. So if I wanted to reduce an acid chloride, I can use the big bulky tert-butoxy delio, and we can get to the aldehyde. If I want to reduce an ester down to an aldehyde, I can use dibol. Any guesses as to which one you think is more likely to show up on any given exam? Really? No guesses? No ideas? Should we try it again? Lithium tri-tert-butoxy aluminum hydride or dibol? Dibol is super, super common. Shows up pretty much everywhere, so watch out for that. Okay. Can we further, let's see, did I actually make a slide on this? I didn't. all I ended up saying was regardless, look for the metal hydrogen bond or metal hydride bond. Okay? So if you take a look on the internet for reducing agents, you will find that we can change the ligands, in this case our T-butoxys or our isobutyls. We can change those ligands, which then changes the reactivity of that hydride molecule. So we end up doing different reductions for those different species. While you are not directly responsible for knowing what those reagents do, you are responsible for looking for that metal hydride bond. So if you see a metal hydrogen bond, you should immediately be thinking in the back of your head, reduction, do it. Okay. If it's not one of the standard ones, lithium aluminum hydride or sodium borohydride, not only should you be thinking reduction, you should be thinking not complete reduction. Okay? The reason we're changing the structure is to prevent the full reduction. Okay, so watch out for those kind of weird things potentially popping up, more so on the ACS exam than on anything I would write or what you see in the textbook. Okay? Carbon nucleophiles. Okay, just like hydride, we've got really strong nucleophiles in our Grignard reagents, okay, or our Gilman reagents, or even our alkyl lithiums. If we add the methyl Grignard reagent shown to an acyl chloride, what do we end up with as a product? As a big hint, not the answer shown. As another big hint, those of you in lab did this experiment. And before someone calls me out on where did that hydrogen come from, the nucleophilic addition happens twice. In the first step of our reaction, we get a nucleophilic addition and elimination of the chloride. In the second step of that reaction, we have just a straight up nucleophilic addition. Standard stuff from the previous sections. Okay. The Grignard nucleophile is such a strong nucleophile that it is very hard to stop it, and you'll end up seeing multiple nucleophilic additions to our new carbonyl compounds. Okay. This holds true with our esters as well as our acid chlorides. The acid chlorides we might predict to be even more reactive. The esters actually have an even further interesting feature behind them. The first product produced in both of these cases is what? We did a single nucleophilic addition. We'd end up with what functional group? Not ester. We would have a ketone. I didn't say no to you. I said not ester. Didn't I say not ester? Okay, just checking. We ended up with a ketone. Okay, well, the interesting feature with our ester reaction, what is the relative reactivity of our ketone versus our ester? The ketone is actually more reactive than the ester. The acid chloride we don't have quite as clean an explanation for why it continues to go through and add. But in our first reaction with our ester, it should add a second time because our first product is more reactive than our starting material. It should do another nucleophilic addition. With the acid chloride reaction, we form a ketone, which is more stable, the ketone or the acid chloride. The ketone was more stable than the acid chloride. So we might have predicted a reaction stalling at the ketone. Turns out we can't control the equivalence well enough, and we end up continue to get more substitution or more additions. Right? I don't know that you guys actually need a mechanism. Do you guys need a mechanism? Should we actually walk through that whole thing? Okay. I didn't really think you did, but if you wanted to, that's fine. You've got the steps drawn out. It's the same thing that we started off this whole chapter with. Nucleophilic addition, tetrahedral intermediate, destroy the tetrahedral intermediate, kick out your leaving group, we've got a product. Okay. And then it can continue to react according to the material from chapter 17 and 18. Okay. The lithium dialkylcuprates go through and continue to react. You'll notice that they have an interesting feature. They actually stop at the ketone. Why do they stop at the ketone? Where do our lithium dialkylcuprates react? They are known for their beta attack on alpha-beta unsaturated carbonyls. We don't have a beta position. Their nucleophilicity is low enough that we can actually get them to halt at the ketone process by being very careful with the amount of reagents that we go through and add. Okay. Kind of a neat little function on those. I keep trying to put this slide in, so it's here, but really officially I think this is best suited for the end of chapter 21. Which means we're down to like 3 slides. Holy crap. Most of chapter 21 is a review. Like, I started flipping through the slides. I can find 10 slides out of 60. Yeah, about 10 slides out of 60 that is not just straight up review. Okay, we've already talked about them in detail. I've not posted those slides yet because they aren't done. But I will try and get those posted sometime soon. What we have on this slide is something that's referencing the interconversion between all of these. Notice through the very middle we've got our acid chloride with a nice little useful information at the top that it's most electrophilic. And we slowly drop all the way down to our least electrophilic with the carboxylic or carboxylate. The ester, you'll notice, roughly equivalent in reactivity to the carboxylic acid. Why roughly equivalent? What is the difference between an ester and a carboxylic acid? Carbon versus hydrogen. Not only is it carbon versus hydrogen, it's carbon versus hydrogen in a secondary fashion. It's not even directly connected to our electrophile. Okay. So what is the difference between carbon and hydrogen? Not much. Which means, is there much of a difference between an ester and a carboxylic acid? As far as the electrophilicity goes, not really. Okay. The carboxylic acid kind of has a trump point in it. What's its trump point? As a hint, the name kind of gives it away. It's an acid, which means if I add a strong nucleophile to an ester, the nucleophile attacks the carbonyl. There's really no question. If I add a strong nucleophile to a carboxylic acid, that nucleophile can act as a base, which then means I'm not looking at the reactivity of a carboxylic acid anymore. I'm looking at the reactivity of a carboxylate. So we have to be careful when doing chemistry with our carboxylic acids as electrophiles because it is very possible to convert them into carboxylates. As soon as they're carboxylates, we got nothing as far as reactivity goes. Okay? It's very hard to get it further up the ladder as far as reactivity. Okay? So if we start at the carboxylate, you cannot go to the amide. That process is physically impossible. Okay? Nitrogen as a nucleophile cannot actually add to that structure to advance it forwards. The only thing we can do to a carboxylate is to turn it into a carboxylic acid. Once we are at a carboxylic acid, we now have some potential chemistry that we can work with. Okay? It can be converted through equilibrium, and this is where our equilibrium reaction kind of sucks, but it can be converted into an ester. So very strong equilibrium-driven reaction requires lots of Le Chatelier's interpretations to watch out and balance that. Okay? You'll notice that when you look at those reagents, to go from the acid to the ester, it says catalyzed by only acid. But to go from the ester to the acid, I can use acid or base. Why the difference? A base deprotonates the acid, and that takes us to the carboxylate. The carboxylate we can't do anything with. Okay? Once we're up in this situation, from our acid, we can go down relatively easily. We can go down to our carboxylate. You'll notice that we don't have a down arrow to the amide. Why not? What would the nucleophile be to generate an amide? We're looking at a nitrogen nucleophile. What's the issue with nitrogen as a nucleophile? Maybe some people mumbled it out. Let's draw a good old nitrogen nucleophile. What nitrogen nucleophile is this? Ammonia. What's the issue if we try to use ammonia with carboxylic acid? Generate the amide. Ammonias are, or nitrogens are bases as well as nucleophiles. So I can't go from the acid to the amide because I do the acid-base reaction instead. Okay? And then I'm again screwed in back to the carboxylate. Okay? The one advantage that the carboxylate has that none of the others have is this arrow on the far right. What is that far right arrow going to? It is creating the acid chloride, the most electrophilic within this sequence. Okay? I cannot make the acid chloride from any one of the other acid derivatives. It has to come from the carboxylic acid. What chemistry am I using to get it from the acid to the acid chloride? SOCl2, which is what chemistry? It's not really a yelid. Substitution. That's converting an alcohol into a chloride. Okay. Officially, we can convert an OH into a chloride. In this case, we're converting a carboxylic acid, OH, into a chloride. It's standard substitution chemistry. The sulfur acts as a really good electrophile. The oxygen attacks the sulfur, kicks out the chloride. We now have a good leaving group. Chloride comes in, kicks out the good leaving group. Straight substitution all the way through. Okay. So now that I've gone from the acid up to the chloride, now where can I go with the chloride? Anywhere I want. Okay. It's something that can move around really freely. I wish I had a better analogy, but that's all I got. Okay. So we're at the pinnacle of reactivity. I can take that down into any layer below it by adding the appropriate piece to make that functional group. Okay. To form our anhydride, all I have to do is add the least reactive of my species, the carboxylate, and I can get to my anhydride. Or I can add a straight alcohol, and I end up with ester. Or I can add some kind of amine structure, and I end up with my amide. Okay. When you are looking at the reactions coming out of this chapter, you may very well see steps within these. They may ask you to go from the anhydride to the acid chloride. Ooh, that's challenging. How do I go from the anhydride functional group to the acid chloride? Is there any direct path? I can add water, which will take me to the carboxylic acid. Once I have the carboxylic acid, then I can add the thionyl chloride as a second step to do the reverse. Okay. So depending on where you are within that system, we may ask you to go to a higher energy state. We may ask you to go to a lower energy state. Okay? And yes, you do have to follow these circles fairly frequently. Okay? Questions? Can't remember if I got this out of the textbook or not, but it was kind of a nice spider diagram that shows all the potential reactions that we can get. You've got your alcohol with an acid chloride going out to each of your individual species. So you can react with alcohols, your amines. Notice that they somehow, for some reason, branched out the amines into primary, secondary, and tertiary because we're generating then variously substituted amides. Your lithium aluminum hydride can take you out to your straight up alcohol. Our big sterically hindered aluminum hydride structure can stall us at the aldehyde. We've got some Grignard reactions coming through to our alcohols. We also have the Gilman stopping at our ketones. Okay. How can we make the chloride? We've got that nice little addendum at the front. Okay. So I thought it was a nice little summary. I don't really see the point of putting in all the other ones because all the other ones show the exact same thing. All you do is just substitute a different structure in there. Okay? Chapter 21, I did apparently luckily grab a few slides from chapter 21 that I liked. It is mostly a repeat of chapter 20. Okay? The primary focus in chapter 21 is really looking at the interconversions between all of those. How do we organize ourselves back and forth between those and the mechanisms associated with each of those? Well, the mechanism's the same. The nucleophile attacks. We break the pi bond. We form the tetrahedral intermediate. We then kick out the leaving group when we reform the pi bond. Okay. One thing that's going to become a little bit trickier, particularly when it comes to mechanisms in chapter 21, is they're looking at weak nucleophiles, which means no base. We're looking at primarily at acid catalyzed mechanisms, which means lots of protonation, deprotonations within your mechanisms. You'll put on a proton to activate the electrophile so the nucleophile can attack. Okay. Tetrahedral intermediate. Kick out the leaving group. Now you got to deprotonate to get back to your carbonyl structure. Okay. So that's the primary mechanistic issue within 21 is lots of protonations and deprotonations at the different stages to say, okay, this is why this one advances, why this one advances. Right? One of the things they go through and do is look at the reactivity of the carbonyl compounds again in more detail. You'll notice we've already talked about this. In this case, though, they are introducing a new term that seems to confuse people, so I want to draw attention to it. That new term is hydrolysis, which means water cutting. Is how I would look at it. Okay. So water is coming in and cutting something. What is it cutting in the acid chloride? The chloride bond. What is it cutting in the anhydride? The CO. Okay. What would it be cutting in the aldehyde or the ketone? Careful. Nothing is a bit dramatic. The pi bond to form the hydrate. Okay. Not a favored structure, but that is what water is doing. It is reacting with that pi bond. Okay. And our acids and esters, we end up doing the same thing. We're talking about how does water come in and cut those individual bonds. Okay. Where this is more relevant is not so much the water cutting or the hydrolysis, which it sounds like some of you at least heard, but the next big term, oh crap, Solysis, Solysis, I think I got that right, which is now solvent cutting. typically when you're looking at solvent cutting, your solvent is some kind of alcohol, which if you blur your vision really carefully and pretend I'm not erasing things, that looks an awful lot like the same thing that's happening when we do hydrolysis. Okay. And actually I erased the wrong part, but it's the oxygen acting as a nucleophile and the rest of the chemistry that follows with it. Okay. So that's what's happening when we're looking at our hydrolysis or our solvolysis. If you go through and look at the reactivity of these, the rates for hydrolysis with our chlorides and our anhydrides, incredibly fast. Why are they incredibly fast? What? All the other ones have polar bonds, so don't quite accept that.
What's the most reactive one?
Those are more reactive ones. Why were those more reactive? They don't have the resonance stabilization of the carbonyl that all the other ones do. Okay? So it's the same ranking system that we've been looking at. It's just looking at a slightly better or easier way to visualize. Susceptibility to nucleophilic attack. It becomes more nucleophilic as we move further up because of all those resonance arguments. This becomes a much larger or more prevalent issue within this chapter than in the last one, because in the last one, what they were allegedly officially looking at were strong nucleophiles, hydride, carbide. Do we care necessarily about the reactivity of the electrophile if we've got stupidly strong nucleophiles? Not so much. Okay. Here, it's officially the weak nucleophiles. That's the argument they're now making as it becomes more relevant here. Okay. It's the same pattern in reactivity. I remember attempting to draw this really, really early on. Hopefully you all remember my attempt to draw it. Some of you did. Okay. This is what's happening. Our tetrahedral intermediate is pretty darn close to the same energy for all of these. Okay. But what changes is where our starting material's energy is. The acid chloride is much higher in energy, which means the gap between the intermediate, our tetrahedral intermediate, and our acid chloride is now smaller, which means it's a faster reaction. Okay. The textbook drew it a whole lot nicer than I did, but it's the same idea. Mine was more meaningful because I drew it. Okay, it's the thought, right? That is within 30 seconds, the end of lecture for today.